Okay guys, we are starting a new unit. This unit is on proving trig identities. Just so that you're aware, this unit, Unit 4, which is proving trig identities, and Unit 5, which is trig equations, solving trig equations, are so important to us. They're pretty critical to us that for now until the end of the school year, you're going to have one question on every quiz and test on either one of those topics, either the proving trig identity topic or the solving trig equation topic. There will be one question on every single quiz or test over that topic. That's how important these are. These are critical because they actually are going to help you in calculus. And we can't just learn them now and then completely forget about them, because that would be a really bad idea. So if you're coming in late, grab a syllabus and a gold sheet, syllabus gold sheet. All right, so with that in mind, these the gold sheets that I've given you are a place for you to collect all of the identities and properties that you're going to be using, that you're going to be using in proofs. Okay, that you're going to use these. So this is a place for you to write things down so they're all in one location. I'm not going to grade it. It's just for your benefit. It's to help you. All right, so let's go and look and see what in the world we're talking about. So today's lesson is actually on simplification. A lot of the blanks are going to be filled in today. Actually, these two right here are the quotient properties. So if you look on your gold sheet, the top one, we have reciprocal properties that are listed here. We have our quotient properties, our Pythagorean identities, even odd identities, cofunctions, so forth. I'll give you just a minute or so to copy those down on your sheet, on the gold sheet. So the naming of these things is important. That's why I have the names by there. Reciprocal properties are those top three. Quotient properties are the next two. Then we have Pythagorean identities, even odd identities, and cofunction identities. Okay. Now hopefully you have these printed out. I don't have enough time to allow you to copy them all down. They certainly are online if you don't have them printed out. I do want to start talking about some of them. So I think you're pretty much familiar with the reciprocal identities and really the quotient identities, right? You all have used those before, you know those. The new ones are really the bottom three, Pythagorean identities. Pythagorean identities are one of the most important. They pop up all of the time. I mean, seriously, they do. We just dealt with them in calculus just the other day. So those are critical. What I like to do is I memorize this one. Sine squared plus cosine squared is 1. That's the one that I memorize, because the other two I can generate from sine squared plus cosine squared is 1. And let me show you how I do that. I have, if I can memorize one formula versus 3, I would choose that, because there's a lot of things that we need to memorize. Basically, that whole sheet you're going to have to memorize and keep it in your head, this year and next year. So it'll be critical for you to memorize this. So let's talk about how we can create sine squared plus cosine squared. We can use that to create the other two. So if I take sine squared plus cosine squared equals 1, I take that, and let's say I divide the whole thing by sine squared. Okay, if I divide the whole thing by sine squared divided by sine squared is 1. Cosine squared divided by sine squared is cotangent squared. 1 divided by sine squared is cosecant squared. And you can see that I just generated this one. Okay, I just generated that one without having to memorize it, because I divided each one of those by sine squared. Okay? So what do you think would happen if I divided sine squared plus cosine squared equals 1 by cosine squared? I'm going to get the other one. Let me show you. So let's do the other one. So for me, memorizing this one is really easy, right? I have a hard time memorizing these because I can't ever remember where the 1 goes and which one goes with the 1 and which one doesn't go with the 1. I have a hard time remembering that. So that's why I do this. So sine squared plus cosine squared equals 1. Let's divide the whole thing by cosine squared and see what happens. So sine squared divided by cosine squared is tangent squared. Cosine squared divided by cosine squared is 1. And 1 divided by cosine squared is secant squared. So you see what we did is we just generated this one. So you may use that technique, you may not. It's totally up to you, whatever you want to do. If you think it would be easier to memorize these two, I mean, that would be fine. It's just we have to have them all memorized. Okay? Let's talk about the even-odd identities. I think they're a little bit interesting. So we have sine here. We need to know that it's reciprocal. Cosecant behaves just like it does. So you should probably write this, add this to the list. Okay, because cosecant is going to behave just like sine is. In other words, when we're faced with sine or cosecant of a negative angle, we can rewrite it as negative sine or cosecant of the positive angle. Okay? And cosine and its reciprocal, secant, these little guys right here are the only even ones. So cosine to the negative x is the same thing as just cosine x. And likewise for secant, that's its reciprocal, right? Secant of negative x is just secant. Tangent is similar to these two over here, where tangent of negative x is negative tangent x. And again, its reciprocal behaves the same way that it does. Okay, it behaves the same way. Cofunction identities, they're kind of a bit big and messy looking, aren't they? Really, let's think back to when we were graphing. Recall when we would take a sinusoidal graph, you know, like a curve, and we could either write this as a sine or a cosine. Remember when we were doing that, depending on the phase shift? Right, that's all this is about. If you do this phase shift with sine, you're going to get cosine. I mean, that's all this is about. It's about phase shifting, so they're the same. You know, on cosine, you do this phase shift, you get sine. Notice that the pi over 2 is in the front. That's going to be important to us because later they're going to mix them up and, you know, it'll be either in the front or the back of that, these two terms right here. So those are cofunction identities. And those are the ones we're going to start out with. These are all the ones we're going to start out with. Any questions so far? Today's lesson on simplifying trig expressions, to be honest, I really think that this lesson is more difficult than actual proofs. And the reason is, proofs, at least you know where you're going. Right? You know where you're going. You're going to have, you know, the side of the equation that you're trying to get to. And you know what your goal is. When we're simplifying, we really, the goal is kind of nebulous, so I tried to write it down for us as best I could. What our goal, when we simplify, our goal is to make the expression smaller. I mean, that's our goal. We want to shrink it. If what we're doing causes it to get bigger, then don't do that, right? We want to shrink it. So we would like to shrink it to one fraction or no fractions. We really don't want fractions at all. Okay, one fraction or no fractions. No fractions would actually be the preference. Okay, but sometimes we can't. Sometimes we have to leave it in a fraction. So we want just one or no fractions, and we would really like to just have one kind of, you know, just sine or just secant. So just one trig function. That's our goal. So we need to keep our goal in mind as we're working on simplifying these expressions on, where are we going? How do we know when we're done? Well, we know when we're done when we're as small as possible. That's why I think this lesson really is harder than the other lessons in the unit, because we don't know where we're going. We don't know what it's supposed to look like. All we know is we're supposed to shrink it. We really shouldn't have a fraction if we can avoid it, and we really should be down to one trig expression. That's what our goal is. So with that, I have a few examples on the next page where we're going to practice. And the reason that gold sheet is going to be important to you is because, well, I'll show you. We're getting ready to work some things out that at this point, you've only seen these for a few minutes. You haven't had time to memorize them, right? So you're going to have to refer to your sheet where you have them all listed. Okay, so let's look at the first problem where it, of course, asks to simplify. So we look at that and we think, well, what kind of property did we just learn looks like that? It would be the even-odd properties, right? So I'm going to rewrite this using the even-odd properties. So this is going to be negative sine of theta and then cosine of theta. Now, here's the requirement. I require that you write a reason for everything that you do. Everything. On this, on proofs, everything. We're just going to, I want to be able to follow your work. And as you can imagine, it can be very interesting grading trig, trig proofs from tag students. Very interesting. Some of my tag students can get to where they're going in 3 steps. And some take 15 steps to get there, right? So, but they still get there. It just is a different path. So I have to be able to follow your work, and I want to follow your thought process, right? So what did we just use? I need you to tell me every step of the way what you're using. We just use even-odd properties. So we would write out beside this even-odd. You don't have to use the word property. You can just drop that. You can just say even-odd. Now, some students like to do multiple steps at a time. I understand that, but on each line, a maximum of 2 steps, 2 reasons, no more. I cannot follow if you skip 4 steps ahead. Or I could, but it will take me a while to get there, and that's just not, we're just not doing that, right? Use 1 or 2 steps per line. So for example, here I did even odd. That was just 1 step. We're great. That's fine. Next step, so we have 1 fraction. We really don't want a fraction if possible. We look at that and we think, well, what property might help us there? Our quotient rule would help us. So we're going to rewrite it. It's going to be negative tangent theta, and that would be quotient. Now when we're done, you can, box in that final simplification answer if you want to, or you don't have to. It's just up to you. And that is just 2 steps. It took us 2 steps to simplify that. All right, how are we with that? Okay so far? All right, let's look at the second one. That numerator, that looks familiar, right? That looks like cofunction. That's cofunction, so let's do that. Let's work on the numerator. So that turns into sine. So sine over cosecant by cofunction. Now the great thing about these and proofs is, okay, I love this stuff, right? I love it because we don't have to do it the same way. It's okay. We're going to get to the same goal. We can go a different route. It's all right. Okay, so I would do cofunction first. So then we look at that. We say, well, that's a fraction. I don't really want a fraction. So why don't I, and there's several things you could do. I'm going to think about this as 1 over cosecant. Right, 1 over cosecant. We know that 1 over cosecant is sine. So I'm going to write this sine down, and 1 over cosecant I'm going to turn to sine. And that reason would be, what allowed me to do that? The reciprocal property, right? So I'm just going to write RECIP. That's the reciprocal property. I just abbreviate it. Okay, great. Now we really want to shrink it. Our goal is to shrink, right? So what if I go ahead and multiply those 2 together? And that would give me sine squared. And my reason is simply multiply. I mean, that's the reason. That's what I did. I multiplied. And that's as small as I can make that. Okay, questions on that? Okay. The third one, we're looking at that like, what? What is that craziness, right? I mean, it kind of looks like a quadratic, doesn't it? Kind of looks like a quadratic. And you will be delighted to know that we can factor that. Oh, isn't that wonderful? We're going to get to factor in, with proofs. It's going to be great. That's just what a lovely mixture. Now, there's probably many of us in here that have not factored something that looks like that before. So I'm going to do some sketch work on the side, just some scratch work. We're going to come over here. And I want you to think about this as 2x squared minus x minus 3. Okay, this is just our thinking scratch work. It's not part of the problem. This is how I want you to think if you've never done this before. Think about the signs being just x's. Okay, that's all. And now let's factor that like we would. We would factor a quadratic. Right, that would be 2x, that would be x. I know my signs should be different. One should be positive, one should be negative. Let's see, I know it's 1 times 3, so probably the 3 needs to go there, and the 1 there. Let's see, so let's check that out, make sure that works. So we have 2x minus 3x, yeah, that's the proper factoring. Okay, so what I'm going to do is that's my thinking process, right? That's what I'm doing. But when I go over to my problem, I'm going to go ahead and put the signs in there. I'm not going to put x's because the x stood for a sign, right? So we go over here, it's going to be 2 sine x minus 3 times sine x plus 1 all over sine x plus 1. And my reason is factor. Yep, that's a reason. Okay, how are we so far? I just factor. Now what can we do? We can cancel, can't we? We can cancel. So this goes away and I'm left with 2 sine x minus 3. Now your reason could be cancel, your reason could be simplify. You could write, either one of those is fine. I'll write simplify, but cancel is a perfectly acceptable reason. Now we look at this, we are down to one trig function and we don't have a fraction. And there's really nothing else I can do to that to shrink it, right? There's no shrinking going on, so this is my final answer. Okay, how are we with that so far? Okay. So see, each problem is like a little puzzle all in its own. We just have to look at it and try to figure out which way we're going, what are we going to be doing. Doesn't that sound delightful? Oh, y'all are looking at me like, wow, she's lost her mind. Okay. So last one, let's multiply by the conjugate. Hopefully we remember what a conjugate is. Let's remind you, a conjugate, so we did conjugates, in several instances, like with imaginary numbers, with radicals, different kind of things. So if you recall a conjugate, if we're thinking of imaginary numbers, if I have I plus 1, its conjugate would be I minus 1. Remember that? It was just the middle number, middle sign changed. Some students want to change everything. No, it's just the middle changes, right? So if I'm going to multiply by the conjugate over here, I'm multiplying by 1 plus sine over 1 plus sine. Now this brings up a really important concept for us, and that is these things that we're working with are expressions. They're expressions. We are not allowed to change the value of an expression. We are not allowed to multiply by 2. We're not allowed to square things because we have no way to balance it, right? There's no equal sign. So if we're going to do something, it has to be multiplied by 1. If we're bringing anything else in, we have to multiply only by 1. Now, you can make 1 look pretty much any way you want, and you can even have different ones. As long as you're multiplying by 1, you'll be fine. Okay? So that's what I'm doing here. I'm multiplying by 1. And I'm going to go ahead and multiply it, and then my reason will be multiply by 1. So the beauty of the conjugate, I'll go ahead and, FOIL it all out, right? Because we're multiplying that like that. So we have 1, and then what? Plus sine x minus sine x plus, minus sine squared. Okay, so minus sine squared all over cosine times 1 minus sine. I really encourage you not to distribute the denominator. Leave it alone until the very last. Maybe you'll never have to distribute it. So my reason would be multiply by 1. Okay? Are we okay? So now what could we do? We could just simplify it, right? The plus sign and minus sign, those are going to go away. Okay, so I have 1 minus sine squared over cosine times 1 plus sine. And I just added. You can say add or subtract. I mean, whichever word you want to use. Does anyone see? Now, here is the thing. Let me write this down. Sine squared plus cosine squared equals 1 is a really big deal. It appears all kind of different places. I want you to look at the numerator, and I want you to look at this expression and see if you can figure out what 1 minus sine squared will turn into. Cosine squared, right? If I subtract sine squared over here, don't I get 1 minus sine squared? I sure do, and that's how it appears all the time. Like that. 1 minus sine squared, so that means cosine squared. So we change this to cosine squared over cosine times 1 plus sine, and our reason is Pythag. Very popular reason, Pythag. Okay, does anyone see what I can do now? Can't I cancel? Cancel one of the cosines out, right? So I'm left with cosine over 1 plus sine. And my reason would be cancel or simplify. And then that's as far as I can go. Why would someone do this? I mean, it is fun. But there may be a reason, like in a proof, it may look like this, and you may need to make it look like this. You might be multiplying by the conjugate in proofs. So we're just practicing it. Okay? Yes, ma'am. You just have to know, unfortunately. I wish there was. That's what makes it really hard to simplify, is we just sometimes just don't know if we're done. If we can keep the criteria in our mind, though, is that we really would prefer not to have a fraction, and we really would prefer to have just one trig function, and just kind of think through how we would get there, then that's going to be the most helpful. Okay? All right. Anything else?